All right, we'll begin. Today we're covering chapter 5, which is all about probability. Okay, and so up through last week we were doing descriptive statistics, and beginning this week and next week we'll enter this world of probability. Okay, so this week we're going to cover rules on probability. Next week we'll cover probability distributions, and then after that we'll get into sampling distributions, and that will be begin our entry into inferential statistics. Okay, so what is probability? Probability, this is it's a way to express or quantify how likely or unlikely uncertain events are. Okay, so oftentimes we'll be talking about a random experiment. Okay, and a random experiment is basically it's an experiment or something where what happens next, the outcome, is unknown to us. Okay. And when we talk about the word random, random means that there is we are unable to predict the outcome, and there will be no pattern. There is no recognizable pattern in a sequence of random trials. So we'll say pattern in the outcomes. Okay, so we're familiar with the concept of probability, so we can, simple example. We can talk about a coin flip. Okay, and so when we flip a coin, whether it will land on heads or tails is unknown to us. And if we flipped a coin a bunch of times, we would not expect to see any pattern in the outcomes. Okay. That said, we can still talk about trying to understand a coin flip. Okay, so we might not be able to predict the next coin flip, but we can say after 1,000 coin flips, I would expect something around 500 heads and 500 tails. Okay, maybe a little bit more, maybe 504 and 496 or something like that. Okay, but we would, if we flipped the coin 1,000 times and we got 900 heads and 100 tails, we would feel like something is funny about this coin, that this is not a regular coin. Okay, and so we can still talk about probability. We can talk about the probability of a coin flip. And we can say the probability that the coin lands heads is 1/2 or 0.5. Okay. Okay, and so we, as we discuss probabilities, you know, what does it mean? So here's a question. What does it mean to say that the probability of the coin landing heads is 0.5? Okay, so if we say the probability that the coin lands heads is 0.5, what exactly does that mean? Okay, and so you know, or you know, if I replace the word probability with the word chance or the word likelihood, okay, we're all asking the same question. You know, what does it mean when I say that the coin has a 1/2 chance of landing heads, or that the likelihood that the coin lands heads is 0.5? You know, what do these things mean? Yeah, so what does it mean to say that the chance that the coin will land heads is 0.5?
Half the time they'll land.
So does it mean that half the time it lands heads? So if I flip it 2 times, will I necessarily get 1 heads and 1 tails? Huh? We're predicting, okay. But, so, I mean, just because there's 2 outcomes doesn't necessarily mean that there's a 50% chance of one happening. Because when if we wake up tomorrow, it could either be a sunny day or it could be raining. Does that mean that the chance of rain is 50%? No. Yeah.
It means that it's one of 2 outcomes.
But it's not. It's not. If I mean, there are 2 outcomes. There's heads and tails. It's in this situation, heads and tails are both equally likely, and that's why it's 0.5. But there's lots of situations where if you buy a ticket, there's only 2 outcomes. You either win or you lose. But does that mean the probability that you win is 0.5? No. Okay. So what does it mean to say that the probability that the coin lands heads is 0.5? Okay. So the idea here is we have this idea of the long run relative frequency. Okay. Long run relative frequency. And so here I'm going to make a distinction between what we call an empirical probability and a theoretic probability. Okay. So the long run relative frequency, this will be kind of our notion of probability. Okay, meaning if we flip a coin millions and millions of times, and keep track of all of the results, okay, the relative frequency of seeing heads. So what is relative frequency? You guys remember the relative frequency table? And how do we get relative frequencies? Yeah.
It's a portion of the cumulative frequency.
Right, so it's you know, basically how many times did you get heads divided by how many times did you flip the coin, okay? So in this case would be how many heads divided by how many flips. Okay, so if we flip a coin millions of times and keep track of all the results, the relative frequency of seeing heads will approach 0.5. So, you know, maybe after a million flips, we'd expect something very close to 500,000 heads. Maybe a little bit more, maybe a little bit less, but something very close. And so our relative frequency there is going to be very close to 0.5. So this gets at the idea of an empirical probability versus a theoretical probability. So an empirical probability, this is based on actual random experiments or simulations of random experiments. Is the relative frequency based on actual trials or simulations of trials. Okay, so for example, let's say you had never seen a coin before, okay, and you want to know what's the probability that the coin will land heads. So if you've never seen a coin before and you don't really understand how physics works, one thing you can do is you can just start flipping the coin, okay? And you can keep track of how often you get heads. And so maybe you flip the coin 100 times and you get heads 47 times out of 100. In that case, your empirical probability or your relative frequency would be 47 out of 100. You would have a empirical probability of 47% or 0.47. And based on that, you can say, well, the next time I flip the coin, or in the future, when I flip the coin, I expect that the probability it lands heads is somewhere around 0.47. Okay, and it's not the actual theoretic probability based on math or anything like that. It's just saying, based on what I saw in the past, what I'm expecting in the future is getting a probability of around 0.47 or something like that, okay? And so here I'll write that. So example, what just happened? You know, flip a coin 100 times. Get 47 heads. Your empirical probability is 0.47. Okay, and this is very useful because sometimes we don't have mathematical formulas for everything. So with a coin, it's very easy. We can say there's two sides and they're both equally likely, so the chance of getting heads is one out of two. That's fine. Okay, but let's say you know, you want to know if I send out a bunch of flyers. Okay, so you mail out a bunch of flyers, and you're hoping some people will call your company. Okay, and you want to know, well, what kind of return rate am I going to get? We don't have a mathematical formula that says, oh, based on the neighborhood and based on this, we know exactly what return rate you're going to get. Okay? All we can do is say, well, let's just see. Okay? And you can send out flyers in one area, and you'd get some kind of return rate, and that basically is an empirical probability. Okay? Or it's based on what you've witnessed, you can say, well, I got a return rate of about 2.5% in the past. Therefore, in the future, I'm expecting an approximately about a 2.5% return rate. Okay, that's basically what empirical probabilities are. We either we take historical data or based on actual data, or sometimes we do simulations to try to create a probability for what could happen in the future. A lot of times for sporting events, you can go on a website like ESPN or something, and it will say probability that this team wins. Okay, so like before the Super Bowl, it'll be like the probability that this team wins the Super Bowl is 62% or something like that. How do they come up with a number like that? They run a bunch of simulations. Okay, there's no formula that you can just throw information in and it spits out 62%. They just look at a bunch of simulations. So they might have develop these computer programs that basically play simulated games of football against itself, and they have the computer play 10,000 games against itself, and they see how often did one team win. And maybe in those simulations, one of the teams won 62% of the games. And that's how they get their estimate that says, we predict this team has a 62% chance of winning. Okay, that's an empirical probability. On the other hand, we have theoretic probabilities. Okay, and theoretic probabilities are based on kind of probability rules, on the rules of probability, or what kind of these mathematical rules. Sometimes they're called axioms. Okay, basically they're just rules. And so if we ask, what's the theoretic probability that a coin lands heads? We can say there are two possible outcomes. Heads and tails. Both outcomes are equally likely. So the probability that the coin lands heads is 1/2. Okay. And the rest of our class will focus on learning these rules to get theoretic probabilities. Okay, and so that's what we'll do. So we're not going to focus more on empirical probabilities, but it's important to know that that exists, and they're used quite frequently whenever. So we'll learn all these rules for theoretic probabilities, but really these rules only apply in simple situations. Okay, and sometimes we have much more complicated situations. And so we have to run simulations or do other things to kind of get empirical probabilities to estimate things. Any questions here? Good. Okay, so then let's talk about these rules then. Okay, so we'll talk about the probability rules. Okay, so we have some event, okay, and we'll call this A. Some event A, all right? And so A means we got a certain outcome, okay? The event A means that we saw a particular outcome. Okay, and then so we'll say the probability of A is written as probability of A, like that, okay? Sometimes as with an R in there, okay? So our book uses P of A, but I'd say this also shows up quite frequently in other textbooks and other books as well. Okay, and then so we say the probability of A is a number between 0 and 1. Inclusive. Or symbolically, we would write 0 is less than or equal. Okay, so if you ever get a number bigger than 1 or a number that's negative, you did something wrong. Okay, so the probability can never be larger than 1. Or negative. Okay. We have something called the complement. The complement of A is the event where A does not occur. Okay. And we can call this, we will say probability that not A is equal to 1 minus the probability of A. Okay. So if we say, you know, for example, there is a 10% chance of rain tomorrow, we could say there is a 90% chance of no rain. Okay, so example. Okay, so that would be the complement. So either it happens, if A is, we get some outcome, then the complement of that is not A. So what is, so if we say A is tails, what is the complement of getting tails? It's technically getting not tails, okay? And so, or not getting tails. And so that if we say there's, you know, one outcome is tails, the complement of that is not tails, which includes everything else. And we can say, so that would include, you know, the coin rolls away or the coin gets eaten or something before it lands, I don't know. We can just say, we're going to simplify the world and say if we did not get tails, then that means we got heads, okay? And we can say that. We can say either the coin lands tails, and if it's not tails, then that means heads. And we can do that. That's fine. But the complement of something is technically just not that event. Okay. All right. We have situations where we have equally likely outcomes. Okay. And so, you know, this would be things like, you know, flipping a coin. You have two outcomes, heads and tails, and they're both equally likely. Okay, maybe rolling a fair die. Or maybe drawing a card, a random card from a deck. And all 52 cards are equally likely. Okay, and then so we could say the probability of some event can be calculated as the number of outcomes in the event, or included in the event, divided by the total number of outcomes. Okay, so we could ask, you know, I roll a die. What is the probability I get a number divisible by 3. Okay, so the outcomes in that event would be three and 6. Those are the numbers that are divisible by 3 in rolling a fair die. Okay, so we would have, so our probability would equal number of outcomes in the event divided by total number of outcomes. So we have 2 outcomes in the event divided by 6 outcomes total. The answer is 1 and 3. Okay, or we could ask, what's the probability I get a face card? Okay. So draw a card from a deck. Okay, how many face cards are in the deck? There's 12 face cards. Jack, Queen, and King, each in for each of the 4 decks, or I'm sorry, for each of the 4 suits. So we have 12 face cards total. Okay, so our probability would equal 12 divided by, and how many cards are in the deck? 52. So this reduces to 3 out of 13. And that's the probability of getting a face card. Okay, and again, the key here is that everything has to be equally likely. Okay, this does not work in situations where the outcomes are not equally likely. So, so for example, we could talk about rolling 2 dice and looking at the sum of the 2 dice. Okay, when you roll 2 dice, the sum can be anywhere between 2 through 12. Okay, there's a total of 11 possible sums. Okay, but those different sums are not equally likely. Okay, you do not have the same probability of getting a 2 as you do of getting a 7. Okay, and you don't have the same probability of getting a 3 as you do getting a 6. So those outcomes are not equally likely, and so you cannot say just say that the probability of getting a 2 is, well, that's 1 out of the 11 possible outcomes is 1 out of 11. That's not the case. You'd have to look at all possible dice combinations, and there's a total of 36 dice combinations. Each of the 36 dice combinations are equally likely, and you can then talk about the probability of those outcomes by looking at the actual dice combinations and not just the sum of the dice. Do I need to write that out, or are we just okay with this idea that that this rule of the number of outcomes in the event divided by the total number of outcomes possible only works when we have equally likely outcomes? All right. Okay. Well, we could have another situation where we do have, quote, equally likely outcomes, and they're represented in a table. Okay, so we could have data represented in a table. So for example, we can say do you own a dog? So we'll say owns a dog versus does not own a dog. Own a dog or dogs, okay? And then we'll also have, we'll say owns cat and does not own a cat. I'm just making up information here. Okay, so we'll say 40 people own a dog, 60 people do not own a dog. We'll say 35 own a cat, 65 do not own a cat. And we'll say 22, which means we have 18 over here. 22 and out of 35 means we have 13 over here, and we have 47 here. Okay? So I can ask something like, if I select a person at random from our select a person at random, what is the probability this person owns a dog? Probably should change my numbers here, but it's okay. All right. What is the probability that this person owns a dog? You would say yeah, so we have a total of 40 people who own a dog. 40 own a dog, divided by how many people total in the table? 100 people in the table. So this becomes 0.4. What is the probability this person owns a dog? 0.4. Okay, so I can also write this as probability of dog is equal to 0.4. Alright, so again, I will select a person at random. What is the probability this person has a dog and has no cat? So we would write this as probability of dog and no cat. How many people have a dog and have no cat? 18, okay. How many people total in the table? 100, so our probability here is 0.18. Okay, so what would be probability of dog and cat? (22) divided by 100, which turns out to be 0.22. Is that okay? Haven't lost anybody, right? Okay, let's try another table. Okay, so we'll say left-handed or right-handed. I know there's ambidextrous people, but we'll just say which one do you prefer, and you have to pick one. So left-handed or right-handed. Okay, and then we'll say glasses or no glasses. Okay. All right, and I'm just going to make up some numbers here. 20 and 140, and we'll do 10 and 10 and 60 and 80, 70, 90, 160. Okay, so I'm going to ask just a few things. What is the probability of left-handed? What is the probability of glasses? What is the probability of left-handed and glasses? So I'll give you a minute to punch these out. What did we get? So for left-handed, we would do 20 divided by 160, and we would get what? 0.125? Okay, for glasses, we would get 70 divided by 160. And we get 0.4375. And then for this, we would have 10 over 160, which is 0.0625. Is that okay? All right. We can ask about combinations of events. Okay, so I could say combining events with or. I could ask, what is the probability? You know, I select a person at random from the table. Let me just kind of underline this as a new topic. What is the probability this person is left-handed or wears glasses? Okay. So here the question is, what is the probability of left-handed or glasses? Okay. And when we use the or in statistics, or is always an inclusive or. Meaning it means and or. Okay. So, because in our English language we have there's a slight ambiguity when you use the word or. Okay. So, for example, I could ask you the same question, and the way you would respond would be a little bit different, just depending on kind of the intonation I put into my question. So I could say, do you like, I could say, do you like chocolate or vanilla ice cream? And you would say yes, or you would say no. If I say, do you like chocolate or vanilla ice cream? And then the expected answer would be a yes or no, okay? I could ask the same words, but I could just say, do you like chocolate or vanilla ice cream? And then your answer there would be, I like chocolate, or I like vanilla ice cream, okay? Because you can have an exclusive or where we're asking one or the other. And then we have the inclusive or, which is, do you like one or the other or both? Okay, and in statistics, when we use the word or, it's always the inclusive or. So it's, what is the probability that someone is left-handed or wears glasses, or is both left-handed and wears glasses? Okay. All right, so how can we answer this question? How many people qualify as left-handed or wears glasses? Yeah, there's 80 people. If we look at our table, we'd see we see these 60, these 10, and these 10 people qualify as left-handed or glasses. Okay, so these 10 are left-handed, no glasses. These are left-handed with glasses, and these are glasses but right-handed. Okay, so we have a total of 80 people. So our answer here would be 80 divided by 160. We have a total of 0.5. Okay, that's one way to do it, is to look at the table. Another way is we can say, well, how many people wear glasses total? Okay, 70. How many people are left-handed? 20. Okay, now if I add 70 and 20, I would get 90. Okay, that's too many people. What I've done wrong is I've double counted this. This 70 includes the 60 and the 10. This 20 includes this 10 and this 10. So when I add the 70 and the 20, I'm basically doing 60 and 10 for the 70 plus 10 and 10. So I've double counted this 10, so I would have to subtract that overlap. Okay, so another way is I could say probability of left-handed or glasses, this is equal to the probability of left-handed plus the probability of glasses, but I want to subtract off the overlap. Okay, and what is the overlap? The overlap is left-handed and glasses. So this becomes 20 out of 160 left-handed plus the 70 who wear glasses minus the overlap, minus the 10 people who got counted twice. And this would also give me 80 out of 160, and this is also 0.5. Is that okay? Okay, let's see if we can put this all together. All right. Okay, so I'm going to just make a few statements. We'll say we have the probability that someone I don't know, has brown hair is 0.4. Okay, and we'll say the probability someone has blue eyes is 0.25. Okay, and we'll say the probability someone has blue eyes and brown hair, is 0.15. Okay, so I'm going to ask, what is the probability that someone does not have brown hair? Okay, so probability of not brown hair. I'll ask just to, I'm just going to put this symbolically. I'll put probability of brown hair or blue eyes. Okay, and I'll pause here, and I'll let you guys work on these ones. Okay, so walking around, I know a lot of you guys got it, and have done it, and some of you, I'm not exactly sure what what you were doing, and just I mean in terms of like, you know, not even, it doesn't seem like you were taking notes in class, and I'm not sure. Yeah, well. You know, you don't have to take notes. There's no requirement, but I at least encourage you to try out these problems when I put these up here. Okay. All right. So what's the probability that someone does not have brown hair? Okay. So we said, well, probability that someone has brown hair is 0.4. The probability that someone does not have brown hair is going to be 1 minus 0.4. So 1 minus the probability of brown hair. And so that will be 1 minus 0.4, which gives us 0.6. Okay. As far as brown hair or blue eyes, we can write this as probability of brown hair plus the probability of blue eyes minus the overlap probability of both brown hair and blue eyes. Okay, so this would give us 0.4 plus 0.25 minus 0.15. So we have 0.65 minus 0.15, a total of 0.5. Okay. Just want to pause here and make sure everyone's okay with this. All right. I'm going to, you don't have to copy these over, but I'm going to create a new slide here. Okay. And we could say, I could ask a question. What is the probability someone has brown hair and eyes that are not blue? Okay. What is the probability that someone has brown hair and eyes that are not blue? And in order to answer this question, I would say we should probably turn our information up here into a table, okay? Or we could also make a Venn diagram, and I'll show them both. Okay, we could have, so I'm going to just have brown hair and not brown hair. Or you can have, and you can have blue eyes or not blue eyes. Okay, and the way you set up the table is arbitrary, whether you put hair color on the side and eye color up top, or you know, make eye colors the columns and hair color the rows. that doesn't matter. In my case, I happen to make hair color the columns and eye color the rows. Okay, so brown hair, we have a total of 0.4, which means not brown hair must be 0.6 because we're going to add to 1. Blue eyes, we have 0.25, which means not blue eyes will be what? 0.75. And I have one number that goes here, and what's that? 0.15, right? So if I have 0.15 here and I've got 0.4 total, how much goes right here? 0.25. If I got 0.15 here and 0.25 here, I've got to have 0.1 here, and I've got to have 0.5 there. Okay. All right, so to answer the question, what is the probability that someone has brown hair and eyes that are not blue? What is our answer? It's this number right here, 0.25. Is that okay? All right, great. Okay, we can also do as a Venn diagram if we wanted to. And you don't have to. If you don't like the Venn diagram, don't worry about it. Okay? So I'm going to have one circle for brown hair, one circle for blue eyes. Okay? And we know that the overlap between brown hair and blue eyes is what? What number goes right here? 0.15. Okay? And we know that the total size of the blue eyes circle is going to be 0.25. So if I have 0.15 here and the total circle is 0.25, how much goes over here? 0.1, right? So that the circle, both this part and this part add up to 0.25. Okay? And then how much is the total brown circle for brown hair? 0.4, which means how much goes here? 0.25, okay? And so if we add these up, we get a total of 0.5, which means on the outside of everything, we're going to have 0.5, okay? And so we can see actually these four numbers appear also in our table, okay? So whether you make the table or a Venn diagram, you have the same information. And some people prefer one over the other. I'm not going to tell you which one you have to do. But just be aware that these are tools that are useful in figuring this out. Okay. All right, so kind of to summarize all of this, we have the probability of A or B is equal to the probability of A plus the probability of B minus the overlap probability of A and B. Okay. We have a special case. All right. We have a special case where probability of A and B equals 0. What does it mean for the probability of A and B to equal 0? What is the probability of A and B? That's the overlap, right? Okay, so when probability of A and B equals 0, that means there is no overlap. No overlap between A and B. Okay, so we would say here A and B are mutually exclusive. So for example, examples of mutually exclusive events. Okay, let's say you draw a card. We're going to say A is the card is a heart. And B will be the card is a spade. Okay? There is no overlap between hearts and spades. Okay? There's no card that is both a heart and a spade. Okay? So these are mutually exclusive. Okay? On the other hand, let's say we draw a card, and I'm going to call event C will be card is heart, and D will be card is a king. Okay? These are not mutually exclusive. There is overlap. And what's that overlap? The overlap is the king of hearts. Okay, so there is a card that is both a heart and a king. So C and D are not mutually exclusive, whereas A and B are mutually exclusive. Okay? And so in that special case, the probability of A or B is equal to the probability of A plus the probability of B. Okay? And there's no overlap to subtract. Okay? So A or B, this is kind of the general rule. Probability of A plus the probability of B, subtract any overlap. Okay? In the special case, there's no overlap to subtract. Is that okay? All right, why don't we pause here? We'll take a short break.